Welcome to this explainer. Today, we're taking on a massive, incredibly high-stakes engineering mission. We are going to design a platform capable of serving 10 million massive large language model requests every single day. To pull this off, we've got to look right past the quote-unquote magic of AI and explore the intense, hidden engineering under the hood. It's all about serving LLMs at scale.
Okay, let's dive into the architectural blueprint for today. We'll be covering the great memory bottleneck, winning the latency game, clever optimization strategies, sizing the hardware, and finally, scaling to 10 million.
Section 1. The Great Memory Bottleneck.
Right before we can even think about scaling, we've got to fix a fundamental physics problem inside the GPU. We have to talk about the KV cache. So during generation, your model stores previously computed keys and values, so it doesn't have to just constantly recalculate everything from scratch. Imagine the KV cache is like a growing stack of paperwork just cluttering up your desk. As your user's prompt gets longer and longer, as the context length increases, this cache just eats up your precious GPU memory incredibly fast because it grows linearly. And here is our first major hurdle. LLM inference is actually memory-bound, not compute-bound. Because of that massive KV cache, our GPUs are spending significantly more time just moving model weights and cache data around than they are actually doing the math. It's crazy. We end up hitting a memory bandwidth wall long before the GPU's compute power is even fully utilized.
Section 2. Winning the latency game.
So, now that we know our real enemy is memory, let's break down the vital signs of our system's speed and how the user actually experiences that delay. The absolute crucial point to grasp here is the difference between prefill latency and decode latency. When a user sends a prompt, the system first processes it to create that KV cache, right? That's the prefill stage. It's highly parallelizable across tokens. It basically happens all at once. But generating the response, the decode stage, is strictly sequential. Every single new token depends on the ones generated right before it. That means every new word has to wait in line, making token generation a massive bottleneck compared to just processing the prompt.
As the principal architects here, these four metrics are basically our system's dashboard. Time to first token, or TTFT, measures exactly how fast the user gets their initial response, which is mostly tied to that prefill stage. Tokens per second, or TPS, measures how smoothly the rest of the text flows out during decoding. But we also have to look at P95 and P99 latency. These metrics tell us the tail latency experienced by the 95th and 99th percentiles of our users. Enterprise systems have to monitor all four of these to ensure that even in the absolute worst-case scenarios, the system is performing smoothly.
Section 3. Clever optimization strategies.
Okay, so how do we push those vital signs into the green and stop wasting our GPU's potential? Well, look at the contrast between two major breakthroughs in LLM serving. Flash attention improves compute efficiency by optimizing the actual attention computation math. Paged attention, on the other hand, improves memory efficiency by optimizing how we manage those blocks of KV cache memory. Think of it this way. Flash attention speeds up the brain's processing, while paged attention intelligently organizes the brain's memory to stop that growing paperwork from totally cluttering the desk. We can also use this really cool mathematical trick called speculative decoding. Here, a small draft model quickly predicts multiple future tokens. Then, the larger, much slower model verifies them. If the large model accepts those predictions, bam! Multiple tokens are generated in a single step, which massively reduces those slow sequential decoding operations. Think of this like a junior assistant rapidly drafting an email and a senior manager quickly approving it. Though, keep in mind, if the draft model's predictions are frequently rejected, this verification overhead actually outweighs the performance gains and just slows us down.
We can take this even further, We can entirely bypass redundant work through caching strategies. Prefix caching means taking previously computed prompt prefixes and just reusing them across different requests to eliminate redundant prompt processing. Semantic caching goes a step further. If we notice frequently asked semantically similar queries, we just map them directly to an entirely pre-cached response that drastically reduces our inference calls.
Now, when we're dealing with massive documents or incredibly long contexts, we bring in the lifesavers. Chunked prefill means we take a massive prompt and process it in smaller chunks, improving our memory utilization and throughput. We can also use rope scaling to expand positional encoding limits or implement retrieval-based context reduction. That basically means fetching only the information that's actually needed for the prompt, rather than trying to feed the model an entire encyclopedia all at once.
Section 4. Sizing the hardware.
All right, we've got our software optimizations locked in. Now we actually have to physically fit these massive models onto our silicon.
When sizing a massive 70 billion parameter model, you can't just look at the base weights. You have to estimate the KV cache requirements, the precision level, like FP16, your concurrency targets, and your context length. A 70B model running in FP16 will generally demand multiple high-memory GPUs just to hold the baseline weights and the dynamic KV cache simultaneously. It's huge.
And because the model is way too big for a single chip's memory, we use model sharding. We quite literally split or shatter the model weights across multiple GPUs. This forces the GPUs to work together as a unified hive mind to serve the model.
But what if we're using a mixture of experts, or MOE model? Then we use expert parallelism. This is such a brilliant shortcut. The different experts are distributed across different GPUs. So instead of waking up the whole neural network for every single word, only the selected required experts are activated per token. This drastically, and I mean drastically, reduces our compute costs.
Section 5. Scaling to 10 million.
Okay, our model fits on the hardware and our latency is heavily optimized. It is time to unleash this beast into the wild. Imagine you are the principal architect and you have just been given the green light to handle 10 million requests every single day. How on earth do we build the infrastructure to survive that kind of traffic?
Well, to survive this scale, our blueprint requires a totally bulletproof enterprise AWS architecture. We are going to need P5 or P6 family multi-GPU instances, paired with a robust serving layer like vLLM or TGI. To handle traffic spikes, we implement aggressive autoscaling and intelligent load balancing across multi-region deployments, plus RAG integration for fetching real-time data.
And for our serving stack, choosing vLLM gives us a massive advantage. It utilizes that paged attention we talked about earlier for super efficient KV cache management. Combined with continuous batching and memory-efficient scheduling, it achieves significantly higher throughput and drastically maximizes our GPU utilization compared to traditional setups.
But, at the end of the day, we must act like accountants just as much as engineers. The math is totally unforgiving. Your inference cost per request equals your GPU hourly cost multiplied by inference time plus your infrastructure overhead plus your token generation cost, all divided by your request volume. Optimizing absolutely every variable in this exact formula is literally the only way our 10 million requests won't completely bankrupt the enterprise.
Which leaves us with a really fascinating architectural paradox to ponder as we wrap up this explainer. As we push GPU physics to their absolute limits, constantly optimizing caching and sharding models across massive multi-region clusters, at what point does the sheer infrastructure cost of generating AI intelligence actually outweigh the value of the answer it provides? It's the ultimate question for the future of scaling AI. Thank you so much for joining me, and keep exploring.